discard those energy levels, you no longer satisfy the differential equation that defines the PV particle, right? So the way in which you get that spectrum is you solve a first order differential equation in lambda, right? It's dz d lambda equals spectrum. If you just say, okay, let's throw away the complex energies that contribute to z of lambda, then you no longer satisfy that differential equation, right?
Why is that? I'm just saying this is an explicit solution to that differential equation.
Yes, but if you throw away, yeah, you're essentially adding some in this solution. If you throw out the complex energies by hand, you're adding some theta functions to the solution, right? You're saying that z of lambda is not the sum of e to the minus beta times those energies. You're saying it's a sum of e to the minus beta times those energies times a theta function in the argument under the square root. And the theta function doesn't satisfy, it's not a solution to the differential equation. For instance, your z changes discontinuously as a function of lambda.
Okay.
So then dz d lambda has points where it blows up, and the right-hand side of the PV bar flow equation is always finite.
So you're just saying PV bar is wrong?
No, I'm saying that throwing out the, I thought that you mentioned that you can discard the complex energies. I'm saying discarding the complex energies no longer is compatible with the PV bar
No, I'm really
deformation.
confused because this deformation can be done level by level, right?
That's right, but the differential equation is not level by level. It's a differential equation for the partition function, which is a sum over levels.
The trace flow equation gives us the differential equation for each energy eigenvalue.
Yeah, I think that's after you do I thought that the observable that you start with is you put your 2D CFT on a torus and turn on this deformation, and you compute the derivative of your partition function on torus with respect to lambda, and I forgot what that's equal to the expectation value of PV bar on the right hand side.
I just solved this equation, right? I mean, this is an operator equation, and we can put energy eigenstates on both sides, and there is a factorization property of PV bar that people use in order to derive that differential equation. I agree that the original we started the action is logarithmic, but I think looking at this equation, if we agree on this, I think we get this solution to be true level by level. But I should think more about it.
Right, I guess that you're not saying that, you're saying that at some point you just discard some of the levels. So you're no longer solving, if you even want to solve the differential equation level by level, at some point you're no longer solving the differential equation for the level that becomes complex. And the signature of that is that in the flow that's typically derived for the partition function itself, you're no longer satisfying the differential equation that
Yes,
defines the flow.
I think I agree. But at least I think, let's say that there's a maximum parameter y that I want to reach in my deformation. I think there is a set of states that we can continuously deform and still keep in the in that way have a truncated diversities. At least that's how I understand.
Thank you guys for talking. And basically, exactly how do you get the? Is there a range of parameters that you can use to not get complex energies, or the complex energies over which you
No, I think for given y, even for small y, we can always have a maximum enough in the state. So there's a tower of energy levels, let's say. For each E naught, we have this deformed formula. So even if you deform there are some nuts that are originally in the spectrum that make this spirit.
Provided that there are arbitrary magic on the okay.
That happens for the opposite sign flow. Like if you in the opposite sign flow, then it's the ground state that first was complex and there's some finite range at which that happens. For holography, this is the sign itself.
So what is the advantage of doing this with respect to like putting a cutoff in the boundary?
What is the advantage of that?
Yeah, of this deformation with respect to just having a physical cutoff in space, for example.
That's maybe on the gravity side of the bulk side you're asking.
Maybe both. Yeah.
I'm not sure how to think about the physical cutoff on the CFD side. Because
Just some night scale.
I see. Right. I think it's because lambda is a dimension parameter, and you're just saying you cannot make it arbitrary.
I mean, in that case, you also get a cutoff in the energies.
Uh-huh.
And,
Shouldn't it
I mean, the energy levels do not flow. You just get rid of more and more as you increase the cutoff.
There isn't a difference that in that case you get not a unique complete theory that is cut off
I mean, but here,
because it is cut off.
the TVR is not UV complete, it's not irrelevant information.
Yeah.
But I think it would flow to a.
If you get rid of the complex eigenvalues, I think it's not even like a local theory. This is what Luca was saying.
Maybe I didn't understand. I think I agree with you.
Isn't there a hope that maybe there is it's sort of in the bulk, if you wanted to match some covariant prescription, that's its intention, it's like putting some manual cutoff on a lattice scale.
Okay.
And it's like a dynamical way of imposing that's the one.
But if we look at the story on the bulk side, here I'm showing the family of geometries of ETZ geometries labeled by this mass parameter. So the story is that there is a radial cutoff at some radius that corresponds to the boundary size of LC cutoff. And the main character here is the Reynolds-Brandon stress tensor that enters into a trace flow equation that is derived by the radial component of the Einstein equation or the Hamiltonian constant of the radial equation. And that trace flow equation is exactly the trace flow equation from the safety side if we appropriately match this stress tensor to the deformed theory stress tensor. And there is a dictionary between the boundary theory and the bulk theory that is given by relating the radius length in the bulk to the central charge of the original CFD. And that dimensionless parameter y that is defined on the boundary translates into this combination of lengthnesses. You see changing y, increasing y corresponds to decreasing LC, so bringing in the boundary, something it's called. And from this stress tensor to compute the quantum local ground mode energy, you find that the deformed energy or the dress energy and the finite cutoff LC is given by this formula, and again there is a maximum mass that you can put here in order to have a finite energy, real energy, and that corresponds to, like, if you have a finite cutoff, you cannot increase the black hole mass arbitrarily because eventually the horizon radius meets the boundary. So these are the correspondence between the boundary and the language. So the key property that is going to play an important role here is some universal band of energy that were existing in the original CFD around this value of delta. that obey Carnot formula, and around this energy, the entropy that we compute. Sorry, question?
I just wanted to ask about the previous slide. Is there like any interpretation of those complex energies in the boundary side in terms of like bound states versus scattering states in the both for like this box of finite length LC?
I don't know that language, but I've heard people talking about going inside the horizon. Maybe that's what it is.
I don't know.
The boundary just become the space like like instead of time like.
Right, that's what people discuss, but I don't know how, I don't know how to think about that because as I'm gonna emphasize later, this is not bringing in a boundary in a pre-existing solution. So we fix some boundary condition and then we look for solutions. So if we fix some condition or a convex boundary, I don't know how to incorporate geometries that have a boundary of the spatial space inside the horizon.
I think I was thinking of something simpler, just like if I'm trying to do like quantum mechanics in some like finite potential well, like can I think of these as like the states that stay real as the states that are like well localized in that well, and states that end up complex from the perspective of someone in that well, the states that are like, you know, localized outside, and so they look like complex as opposed to something else. I don't know if this is like sensible.
I haven't thought about this enough to say whether that's the right answer, but that's interesting. Yeah, so
So in this case, the boundary conditions are the issue,
right.
but wasn't this like, we heard about this conform boundary conditions because of the issue problem, because like ill-defined.
Oh,
Is that
they're not
different?
defined in all situations. In particular, if you have a cylindrical boundary, I think it was shown that they're okay.
Okay, so this setup is.
Also in 3D, everything is much more better.
Okay.
Impositiveness of the Richter condition appears in 4D envelope, I guess, for most cases. And it's tied to the fact that in 3 dimensions we don't have gravitons. So those modes that make the Richter problem unstable are there. Anyway, okay, so look out for this bound domain because that's going to be important, especially when we do the same thing for the decider case. Okay, which is what I'm going to talk about now. So, motivated by the previous work in APS, we will consider adding a new deformation which is called lambda 2, and that's because in the 2D action, it appears as a constant. So it's like it looks like a two-dimensional cosmological constant that you add to the action. And it is parameterized by this eta. So if eta is 1, we get the previous deformation that we had before. And on the gravity side, eta appears in the bulk or 3D cosmological constant term. As I said, for eta equals 1, we have the APS. For the decider case, eta is minus 1 as a replacement. So the idea is to use this deformation instead and solve the energy eigenvalues again level by level. Not over the carrier. We are again discarding complex energy levels. So the first part of this trajectory that is giving us patches of the Sirius space starts with actually APS. So we start with eta equals 1, so we neglect this term for now, and deform the theory to some value of y, this dimensionless parameter. So for the first part of the trajectory, we have this previous formula that we have, and we deform the energy band around c over 6 from y equals 0 to some y naught, which is a non-zero value of y, so that the square root here vanishes. And geometrically, that corresponds to the fact that that horizon radius of the BTZ becomes very, very close to the boundary that is at fixed LC. And there is this remarkably simple geometric observation that takes us to the de Sitter space. And that is, if you zoom in near the horizon of the BTZ, the geometry is not distinguishable from the near horizon region of a cosmological horizon with the same length. L previously was the ADS length, now it's not the role of the de Sitter length. So that's why we focus on this band of energy, because on the bulk side they correspond to a BTC with this horizon radius. So I find it very fascinating that this geometric observation is going to take us to the de Sitter case. So we go all the way close to the BTC black hole, and then we don't distinguish it with the cosmic horizon, and then we continue the deformation with now eta equals -1. So we go all the way and then turn on this term with a different value of eta, which is eta equals -1. Yes. So at that point, the value of that deformation parameter y is some non-zero value, y naught. And then if you solve the energy or the trace flow equation for the energy eigenvalues, this would be the solution. It's important that there are two signs in the square root, both are the solutions. And when you are very close to the BTZ horizon, as I was saying, you do that such that this square root vanishes. And now when you turn on the new deformation, you are bringing in this square root again, but now with the opposite side. So that the formation remains continuous. The fact that both signs are solutions to the trace flow equation can be understood from the geometry by noticing that if you fix the Dirichlet boundary condition, you can have either sign of the extrinsic curvature on the boundary. So there are two possibilities. And as I was emphasizing before, we are not bringing in the boundary in a solution that already existed. We are fixing the boundary condition and looking for solutions that match those boundary conditions. So you can also, the way that it works, it gives you some bounded patches of the Sitter space that is between the horizon and this boundary that we were moving or changing the size of. You can also start with a different value in the seed theory and construct the other side of the boundary in the Sitter space. And if you capture both these solutions in your theory and also in the Hamiltonian, you get all these states on the state that is called the pole patch or the cosmic horizon patch. You have all these states in your theory, and since we are neglecting or discarding complex energies, there is a finite spectrum, so you can think of it as a type 1 operator algebra that exists at finite G-meter. So far we've been talking about pure gravity, and this deformation gives us the gravitational sector. We can add matter fields to the deformation. So the rough idea is that in the CFT side, we need to add something of this type, the boundary operator that corresponds to the bulk radial derivative. So if phi is the bulk field, the boundary operator that corresponds to this bulk field is the radial momentum of the bulk field. And one quick reason to see why this should work is that, like, maybe go back to the ADS case for a second. There, when we solve for a scalar field in ADS background, there are always two types of solutions. One is the normalizable one is the non-normalizable one, depending on its behavior at asymptotic boundary. the asymptotic boundary usually plays the role of the source term of the flow theory. And if the value of the field, if the sinusoid is true here, the value of the field is the source, and if you vary the action on the safety side with respect to the source, we give the operator O. But on the other hand, variation with respect to the field value gives us the momentum kinetic rate in terms of argument. So this is just very heuristic argument to say why the corresponding operator on the boundary should be the radial momentum. And this is in line with the fact that the corresponding operator on the boundary that corresponds to the metric is the stress tensor, and the stress tensor is also the radial momentum of the metric on the boundary. So this is consistent with that as well. But this operator is a little bit badly behaved because of liquid divergences, and the idea is to first do a little bit of TT bar without turning on other deformations, so the theory becomes finite, and then add the extra deformations. And one last thing about adding matter this way is that it only enters into the energy formula. I don't write it on this one here, but it only enters into the energy formula as a factor to the square root. So the finiteness of the spectrum, if you buy the original argument of this starting complex geometry, still remains. And with included matter, the expected thermodynamic behavior in this theory is met. Like you can have a first law with the Robinson of temperature, with the entropy of the cosmic horizon and stuff. So now we're going to go beyond one single patch of the specific matter, and we'd like to understand semi-classical status space holographically using the boundary theory that is deformed from the original CFD. And the idea is to take, for now, 2 copies of these theories that have finite Hilbert spaces and kind of join them such that the semi-classical state on the curve is a smooth geometry. And the total energy is the sum of the 2 Hamiltonians that match the sum of the boundary and the 2 boundaries. One specific state that we can build by taking 2 copies is something like the thermal double state, and that corresponds to the empty de Sitter space. Here I'm going to discuss a feature of this thermal double state. So if we start with this at some time of temperature, so these are the energy, deformed energy ion states that we have from the deformed CFD. And there is this normalization factor here. And the idea is that there is, so the spectrum of energies consists of a lot of states at some maximum energy. Remember, there's a maximum energy, so everything is really relying on having a maximum energy. So if you don't buy it, this doesn't make sense. But there is a maximum energy, and there are a lot of states, large number n max of states that have approximately the same energy, maximum energy. And those are the entropically dominant states. So at high temperature, if you count the number of those states, you get roughly the entropy of the cosmological horizon of the galaxy itself. But if you have such a spectrum, it's not that hard to show that this would be normalization factor should be this. And then if you put it back into fixed state, for A goes from A levels those high energy states in the top of the spectrum. So for those parts of the spectrum, you get a nearly maximally mixed behavior here. So I mean, if you trace out the other side, you get a almost maximally mixed state here. And the geometric construction of this state is very much like the eternal radius black hole. And the idea is that the boundary here has the topology of S1 plus S1, so we can think of state configuration that is done on this boundary by the Euclidean path integral of the boundary theory. And then the usual Euclidean path integral algorithm that leads us to picking something like a harder Hawking set, but on this slice that fills in the boundary. And then if we evolve it, we get the connected geometry of a joint kind of like bounded residual space. We're also thinking about computing entanglement entropy in this context, which can be obtained if we trace out one of the identical systems. This is very much still work in progress, so we don't know where exactly the artist surface is, whether it's in the base here or whether it's somewhere near the boundary. But one observation that we make is that this is just a general observation that if you have a Euclidean problem where we fix the boundary like with the Dirichlet condition and look for the dominant contribution to estimate quantity like log Z that enters into, let's say, Renyi entropy computation that leads to dominant computation. The saddle that we like to propose to estimate this log Z is a local maximum of the configuration space. So that kind of casts out that using this saddle in order to compute some Renyi entropy, for example. So maybe we should turn to number canonical computation. I mean, this Euclidean saddle being a local maximum is a generic feature when you work with classical algorithms in canonical ensemble. So we are trying to see.
Sorry,
whether
can you explain that a little bit? Like, is it because there's like negative modes for the ones that you're trying or?
Yes, non-conformal negative ones.
But weren't those supposed to be fixed by the observer, which is like the boundary here?
They're supposed to be what?
Fixed by the observer.
No, they all satisfy boundary conditions, but they're fixed by the
So there was this series of papers where like, if you have some closed geodesic, if you fix it as the trajectory of some massive particle, then you reduce the amount of isometries that preserve the trajectory, so you get rid of a lot of negative modes of the sphere. And then there's this.
Okay, I'm not putting any massive particle on this boundary.
No, but I mean like the boundaries that you have for the antipodal observers, the cutoff boundaries, those fixed a lot of the negative modes of the one determinants of the sphere. So it's not obvious to me that these are like maximum ones you have to the boundaries.
Okay, I need to, I'm not familiar with that, but I need to understand how that geodesic observer actually acts. Maybe that's our resolution here. Okay. Another aspect of this part reconstruction I wanted to show you was the causal reconstruction or HDLL. So the idea is that for a point in the bulk, we can find the quantum fields on this bulk using some smeared integral of the boundary data. And we need to explicitly calculate this kernel that takes us from the boundary to the bulk. And there is this issue of interchangeability of the mode we perturb the Sitter space with matter, causal reconstruction still works, goes further into the Sitter space, unlike in APS, as I explained now. But let's just consider the Sitter space that is perturbed by matter fields. And these states are some lower energy states in the joint system that we started with. So if you put matter in the Sitter space, there are theorems that tell us there are regions in the space that were previously disconnected from, let's say, an observer that lives on the left boundary, but by adding matter, those regions become accessible to the observer of the left. And this is an example of such a, what we call it, tall Sitter space. This is an example. So we can look at the FLRW geometry with some homogeneous scalar field that is free. So we start with this. And we need to solve the joint equation of the scalar field and the scale factor. If there was no scalar field, the solutions of this would be pure the Sitter space, so we have the Koch. Now, this problem is simple enough that we can solve it analytically, and here is the scale factor. So we see that for the expanding phase, the value of the scale factor is reduced if we pick this constant to be in this range. That means if we compute the duration of the conformal time, which is for the Sitter is pi, that's why we have the square Penrose diagram for the Sitter space. Data goes from 0 to pi, and the conformal time goes from -0 to pi. So the duration is pi. But if we kind of slow down the expansion part, sorry, this is the bouncing part, acceleration. We can increase the conformal configuration. So we get a tall shaped Penrose diagram like this. And there's a boundary that is given by this data that is a function of conformal time and each point. So this was just to show an explicit example of how to do it. And the idea is that the causal reconstruction can still work for perturbed Sitter, because for each point on this quotient slice, we can have causal connection to one of the boundaries. So we can at least build this quotient slice and then find volume to go to the upper part of the boundary. Just to compare with ABS, this is ABS short tune. If you perturb it with matter, there's the length of the borehole becomes larger, and there's a region in the middle of the space that doesn't have any causal connection to the boundary, so causal reconstruction doesn't really exist. But in the Sitter, we have that advantage actually. Yeah, let me just make one final comment about how we are joining the systems together. So we start with two finite spectrum, and these spectrum have all sorts of states in them, like the states with matter perturbations, and we would like to join them together such that the geometry that is a result of this joining is a smooth geometry. And the way to do that is that, again, we only accept those geometries that join consistently from the left and right. For example, if we have some matter perturbation from the left theory that exists in this shared diamond, we only join it together with the right theory that has the same matter perturbation in this overlapping. And that means that if you start with the pure product theory, constraining of the smooth geometries has lower number of states. But I think that's fine, that could still be consistent with having a finite amount of entropy. Yeah, if you have less number of states. Okay. So my point is that even though we have less number of states, we can still produce that entropy. That's the argument. So these are the directions that we are currently looking at, and as you see, these are all like arguments, and we would like to make all these as concrete as possible in order to construct larger patches in the city. So I think I'm gonna leave you with the summary slide, and then thank you for your attention.
Questions for Batoul?
So in the case that you just discussed, where the center diagram is like taller, do the two quantum systems interact with each other? Because there seems to be like a causal contact between the two.
Yes.
Like, do you need to add some interaction?
Right, yes. We have a small interaction there.
And that's like dependent on the state that you choose. Like if you choose empty the center, you should have that thing.
Yeah, it's just.
Has there been any study of a higher dimensional or
They're four-dimensional. Yeah.
is it also exactly solvable or is it not, what are the issues there?
I'm not sure if it's exactly solvable, but, and then, yeah, I don't know what's the status of that.
I was wondering, maybe I missed this in the previous slide, I guess the consistency conditions you have, figuring out which states in the product theory you can consider as smooth geometries, is it just about the value of the matter operator, or is there any other issue? There's no like requirement on the energy on the left, right?
No, it's just, you can have a state on the left that has some matter content, and an independent state on the right. So the different matter content, we are just saying when you are joining them together, they have to match.
Any other questions? Okay, not the second, but again.